Tonight, faster-than-light travel gets treated like a courtroom case, not a fantasy. Nothing can outrun light through normal space, yet space-time itself can stretch, contract, and carry distance with it. That narrow opening leads straight into the Alcubierre metric, the warp bubble, what photons do at the boundary, why negative energy keeps returning, and why causality starts to feel fragile. If calm, rigorous space physics is the kind of thing that helps the mind slow down, tap like and subscribe for more long-form cosmic sleep documentaries. Now let the universe do what it always does: expand, ripple, bend light, and reveal its limits, one quiet idea at a time. Warp drive begins as a quiet claim about distance, not a loud claim about speed. It treats space as something that can be shaped. In a small protected region, nothing needs to rush, a path can be shortened instead. In the mind's eye, the scene is simple. A dark field of faint starlight holds steady. In that field, a smooth oval region hangs like clear glass. Its interior looks ordinary. The strange part sits on its boundary. A thin shell surrounds the oval. The shell is not bright. It is only defined by how the background shifts. Stars behind it appear slightly displaced. The displacements are not random. They form a pattern like a gentle squeeze in front and a gentle stretch behind. The object inside the oval does not move relative to its local interior. The oval itself is what drifts. The first anchor is already present. Motion is transferred from the contents to the shape of space around them. This claim becomes testable as soon as the rule of local light speed is held fixed. In every small neighborhood of space-time, light sets the fastest possible signal. That rule stays untouched in a warp proposal. The interior region is arranged so that a clock there ticks normally by its own measure. A flash of light there still spreads at light speed in that local interior. The early takeaway is calm and precise. Warp drive does not try to outrun light inside space. It tries to move the space that defines the route. Two concepts carry almost everything that follows. One is the metric. A metric is a rule for measuring space-time intervals. The other is curvature. Curvature is how that measuring rule varies from place to place. A warp idea says the measuring rule can be engineered into a travelling distortion. The contents remain nearly inertial. The distortion carries the separation. In general relativity, the metric is not decoration. It decides what a straight path is. It decides what free fall is. It decides how long a journey lasts on a clock. In flat space-time, a straight path looks simple. In curved space-time, the straightest path bends. Light follows those straightest possible paths for light. Those paths are called null geodesics. No special pleading is needed. The same mathematics that bends starlight around a galaxy cluster also bends starlight around any other curvature. A warp bubble is an extreme curvature design. Its interior is kept nearly flat on purpose. Its exterior is arranged to change rapidly. The physical detail that matters is the gradient at the shell. The metric changes most strongly there. That thin region is where stress in the geometry concentrates. A useful everyday analogy can stay gentle. A hallway can be shortened without moving the person by moving the walls. The person does not gain speed. The hallway changes. The analogy is imperfect, but it clarifies the logical structure. The limit is not violated locally. The distance between endpoints is not altered. In space-time language, the interval between departure and arrival can be made smaller along the bubble's route. The bubble does not need to be a rigid object. It is a moving pattern in the metric. This is why the concept is so unsettling. It relocates the question from propulsion to geometry. It asks what rules must be satisfied so that geometry can move as a stable pattern. The Alcubierre construction is the cleanest famous example of that idea. It is not a machine design. It is a metric written down to have certain features. The interior is calm. The shell contains the distortion. Ahead of the bubble, the spatial part of the metric is arranged so that distances contract. Behind the bubble, it is arranged so that distances expand. The bubble's center follows a chosen world line through space-time. The ship inside can be placed near that center and kept close to freefall. The The bubble can be set to move at an effective speed that is larger than light would cover over the same external coordinate distance. This sounds forbidden until the local rule is stated again. No local observer inside the bubble sees a nearby object cross space faster than light. The effective speed is a comparison between far apart events in a curved geometry. It is a statement about a global route, not a local chase. A scale shift makes this feel concrete. Over a few meters, nothing dramatic can be gained. The bubble would barely matter. Over interstellar distances, the difference becomes the entire point. If a route to a nearby star is normally measured in years by light, then the warp picture tries to reduce the distance along the bubble's path so that the travel time by outside clocks can be far shorter. One safe number can anchor this without excitement. Light covers about 300,000 kilometers in 1 second. That distance is roughly 8 times around Earth at the equator in a single second. The number is not used to promise anything. It is used to remind that ordinary speed is already enormous. Warp drive seeks a different lever. It seeks to change what how far means along a route. Now the limit of intuition appears softly because it is easy to confuse coordinates with reality. In general relativity, coordinates are labels. A large coordinate speed can occur even when no local speed is large. The bubble can be assigned a coordinate velocity greater than light. That does not mean an object inside breaks local causality. It means the coordinate grid is slicing spacetime in a way that makes the bubble's center move quickly across the labels. The real test is always local. The local light cones must remain intact inside the bubble. If the interior remains nearly flat, then the local cones look like ordinary ones. In that case, no local message outruns a local photon. Intuition fails when it tries to extend a local rule across a global distortion without checking the geometry in between. This brings the discussion to the first unavoidable accounting step. In Einstein's field equations, curvature is tied to stress and energy. The metric cannot be chosen freely if the matter content is restricted to ordinary forms. A bubble-shaped distortion demands a specific stress-energy tensor. The thin shell is where the stress must live. It is not enough to say space contracts here and expands there. The equations demand to know what energy density and pressure create that pattern. The shell is the place where the requirement becomes sharp. In that band, a component of energy density becomes negative in the simplest constructions. It is not a philosophical claim. It is a computed requirement once the metric is inserted into the field equations. This is the first small payoff. The geometry that seems to avoid the speed limit does not avoid the energy ledger. It trades one barrier for another. A second payoff follows from how the bubble is described. The warp idea is not a singularity. It does not require a black hole. The interior can be flat. The curvature can be confined to a shell. That makes it feel safer than collapse. Yet that same confinement creates steep gradients. Those gradients matter for light, for tides, and for stability. The boundary becomes a physical feature even if it's only a geometric one. A boundary with a steep gradient behaves like a lens with a sharp edge. Light passing near it is redirected. Light trying to cross it may be shifted in frequency. Even before any engineering question is asked, the logic points to photons as the first inspectors. If the bubble exists, photons will map it. The scene returns to the star field and the glassy oval. The displacement of background points is the simplest signature. A clean bubble would produce a clean pattern. A messy bubble would smear it. In this imagined calm, the bubble drifts without sound. The interior stays quiet. No acceleration is felt there. The exterior geometry does the travelling. That separation between local calm and global displacement is the core of the warp promise. It is also the core of the warp fragility. The bubble must be built from a stress pattern that ordinary matter does not like to provide. The boundary must be shaped without tearing causal contact between the interior and the front edge. These constraints do not arrive later. They are present at the beginning. The transition to the next part is gentle. The bubble only becomes meaningful when the strictness of light's limit is understood in local terms. The next step is to hold that limit up close. It becomes clearer why ordinary faster-than-light motion fails. It It also becomes clearer why warp ideas can survive on paper while still feeling physically distant. The speed limit feels absolute because it is not a rule about machinery. It is a rule about which events can influence which other events. The quiet centerpiece is a small burst of light in empty space. The burst begins at a point. It spreads outward as a growing sphere. At every moment, the sphere's surface marks the furthest reach of that burst's influence. Inside the sphere, the burst can touch and change things. Outside the sphere, nothing from that burst has arrived yet. The visual is spare. A thin, luminous shell expands into darkness. No matter is carried with it. Only the boundary of possible contact moves. This is the first steady picture behind the limit. Faster than light travel through ordinary space would mean stepping beyond that luminous boundary while still claiming a normal chain of cause and effect. The structure of spacetime resists that step. A useful term appears here and can stay plain. Light cone means the boundary of possible influence. One sentence is enough for the definition. 2 sentences make it tangible. The expanding sphere is the future light cone of the burst. A matching sphere in the past marks where earlier light could have come from. 1 sentence closes the loop. Everything that can cause the burst must sit inside its past cone. Everything the burst can cause must sit inside its future cone. This is not poetry. It is the geometry of signals when light sets the fastest local messenger. The next part becomes strange only because different constant motions slice space-time differently. Another term can be introduced gently. Inertial frame means a viewpoint moving at constant speed. 1 sentence defines it. 2 sentences ground it. In one frame, the burst happens here and then the shell expands. In another frame, sliding steadily past the same shell still expands at the same local rate. 1 sentence says why this matters. If the local speed of light is the same in every inertial frame, then time ordering cannot be absolute everywhere. The ordering becomes tied to the light cone structure. Events outside a light cone are not linked by any signal moving at or below light speed. They are separated in a way that forbids direct influence. That forbiddance is what keeps cause and effect stable across frames. The first small payoff arrives here. The light limit is not a barrier in space alone. It is the boundary of the only paths that preserve consistent influence for all steady motions. A calm analogy can keep the idea from becoming brittle. Consider ripples on a perfectly still pond. A pebble falls. A ring spreads outward. No point on the water receives news of the splash before the ring arrives. Now, add a steady current beneath the surface. The ring still spreads relative to the water itself, yet the pattern drifts across the shoreline as the current carries it. This is not a perfect translation. It still helps. The ring is the local signal boundary. The drifting pattern is how a different steady motion changes the description. The rule that matters is local. Each small patch of water carries the ripple at the same speed through that patch. Space-time takes the place of the water. Light takes the place of the ripple. The result is that no inertial frame can claim a privileged rest where the boundary becomes different. Any claim of a signal outrunning the boundary in one frame must also survive in all others. That survival fails. The mathematics forces a contradiction. A faster-than-light signal would step outside the light cone. Outside the cone, some inertial frames would tilt the ordering. What looks like sent then received in one description can become received then sent in another. The second small payoff follows with almost no drama. If a usable message could outrun light through ordinary space, then there would exist steady motions where the message arrives before its departure. The ordering of events would not be a shared feature of space-time. It would be a frame-dependent accident. The usual chain of explanation would fracture. A number can enter without becoming a spectacle. 1 year is a gentle unit in astronomy. It is one full circuit of Earth around the Sun. Light uses that unit in a strict way. A light year is the distance light covers in 1 year. The number is not needed in digits. The meaning is enough. The light cone picture scales cleanly from a second to a year. The expanding shell of possible influence after 1 year is a sphere with radius 1 light year. The scale shift lands quietly. What seems small in daily life becomes vast in deep space, yet the rule does not loosen. A signal can fill that sphere in a year if it moves at light speed. Nothing that carries information through ordinary space can fill a larger sphere in the same local duration. The geometry of the cone stays the same at every scale. The limit does not get tired at long distances. It becomes more important. The limit of intuition arrives because the mind tries to picture 4 dimensions using 3. A light cone is not a cone in space alone. It is a surface in space-time. Any picture drawn in space is only a slice. The slice can mislead. In a 2-dimensional sketch, cones seem to tip and overlap like simple objects. In real space-time, the object is the set of all possible signal paths. It does not sit inside space like a tent. It defines what possible means for influence. This is why faster-than-light travel is not merely a faster version of the same trip. It changes which events can be connected at all. Another gentle physical detail reinforces this. The boundary is not a wall made of substance, it is a rule for null paths. Null paths are the routes light takes when geometry is given. If the geometry is ordinary and flat enough, locally null paths form the outer edge of influence. The edge is thin because it is defined by a precise speed. If something could step beyond that edge, while still being a controllable signal, then the edge would no longer mark the limit of influence. The entire cone structure would need revision. The revision would not stay local, it would propagate into every consistent description of time ordering. This is why the limit feels structural. It is woven into the definition of space-time intervals. A quiet refinement prevents a common confusion. The rule is not that light is magically fast, the rule is that light's speed is the same in all inertial frames. That sameness forces space and time to adjust together. It forces the cone structure to be shared. It forces the idea of elsewhere to have a strict meaning. Some events are simply elsewhere relative to a burst. They cannot be reached without stepping outside the cone. Ordinary motion cannot do it. Ordinary signals cannot do it. The price of allowing it is not a slightly stranger journey. The price is the loss of a universal causal map. This is exactly why warp drive turns attention away from motion through space. The cone structure remains local. The interior of a bubble can keep its cones ordinary. The trick is pushed into the geometry between distant endpoints. If the endpoints can be brought closer along a path by changing the metric, then the journey can stay inside the cone at every local step. The next part follows that shift. The limit remains firm inside each neighbourhood. The question becomes whether a travelling distortion can change distances while keeping those neighbourhoods well behaved. Warp drive avoids outrunning light by refusing to treat distance as fixed. The central claim is simple in wording and strict in meaning. Local light speed remains untouched. The route changes instead. A calm scene helps the logic settle. A wide region of darkness holds a faint lattice of drifting dust. The dust forms lines like a soft grid. In the centre, a quiet hollow appears smooth and nearly empty. Around that hollow, the grid tightens on one side and loosens on the other. The tightening makes gaps shrink. The loosening makes gaps widen. Nothing inside the hollow needs to surge forward. The hollow stays calm while the grid rearranges. This is the visual anchors of the loophole. Motion is reassigned from an object to the spacing between places. The first payoff arrives here. A journey can become shorter without any local sprint if the spacing ahead is reduced while the spacing behind is increased. That statement does not defeat the light limit. It uses the limit as a local rule while changing the geometry the rule measures. General Relativity already contains an everyday version of this separation. 2 distant galaxies can grow farther apart faster than a photon would close the gap, and no local rule is broken. In each small region, light still behaves normally. The difference lies in the choice of what is held fixed. If galaxies ride the expansion, they are at rest in a comoving sense. Comoving means moving with the local expansion flow. In that description, each galaxy keeps its place on the local grid. The grid itself stretches between them. The second payoff is quiet and important. Faster than light separation is allowed when it is the stretching of space that produces the separation, not a local crossing of space by a signal. Warp drive borrows this structure and compresses it into a travelling pattern. Instead of a universal stretching, it proposes a localized squeeze and release that moves as a wave. The distinction becomes clearer when light paths are traced. Light follows the geometry it is given. In flat space-time, those paths appear straight. In changing geometry, they bend and shift in timing. A warp bubble is built to keep its interior close to flat. The interior then behaves like a quiet pocket. A flash of light inside still expands as expected within that pocket. The pocket is not the place where the miracle happens. The shell is. The shell holds a gradient. The gradient is a rapid change in the metric across a thin region. The physical detail that matters is how thin the shell is compared to the bubble size. A thinner shell concentrates curvature into a sharper band. A thicker shell spreads curvature more gently. Either way, the shell is the region that creates the effective motion of the bubble. A different analogy can remain natural and slow. Consider a long sandbar under a shallow sea. A tide can shift sand from one side to the other. The shoreline does not need to run to change shape. A channel can shorten when sand accumulates in a narrow bend. The water still flows at its local speed. The path becomes shorter because the map changes. Warp drive uses a similar logic, but with space-time intervals instead of sand and water. The idea is not that space is made of grains. The idea is that the metric defines a map. That map can evolve. The payoff here is that no local law needs to be rewritten if the evolving map changes the length of the route itself. A single number can anchor scale without turning sharp. A light year is the distance light covers in 1 year. That unit marks the ordinary reach of causal influence through empty space. Warp drive aims to reduce an external separation measured in light years into an effective route that is smaller than that same number would suggest. The reduction is not free, it requires the metric to change strongly over a region that stays finite in size. The deeper point is that the local clock inside the bubble can remain gentle while outside clocks register a different comparison between endpoints. The comparison becomes global. It depends on how the space-time slice is chosen. It depends on which surfaces are treated as now across the distorted region. This is the first limit of intuition. There is no single universal notion of simultaneity across a strong distortion. A measurement of how fast between distant points is not a single fact, that is, without a chosen slicing. Local measurements remain clean. Global comparisons gain a dependence on coordinates. This dependence is not a weakness of the theory, it is part of its discipline. Coordinates are labels, the geometry is what has physical meaning. A warp bubble that claims an effective speed is making a statement about geometry and the chosen labels together. The physically meaningful question is more careful. Do local light cones remain intact everywhere an observer could pass? Do time-like paths remain time-like for the contents inside the bubble? Is the interior protected from large tidal gradients? These questions are answered by curvature and by the behaviour of nearby geodesics. The second limit of intuition arrives here. A bubble can look gentle in one description and hide sharp gradients in another. The shell can be made to appear thin or thick depending on the coordinate choice. Only invariant measures of curvature reveal what is truly present. Invariant means independent of labels. If invariant curvature grows large at the shell, then tidal effects grow large there as well. A calm interior does not erase that boundary cost. A micro payoff follows from focusing on what the bubble actually does to distances. Contraction ahead means that successive points in front are brought closer together in the bubble's direction of travel. Expansion behind means that points behind are pulled farther apart. If the pattern moves, it carries the calm interior along without dragging it through ordinary space in the usual sense. The contents stay near the centre of the calm pocket. The pocket rides the moving distortion. The effective arrival time can then be shorter than an undistorted light path between the same distant endpoints. Yet no local message inside the pocket outruns a nearby photon. The bubble avoids a local chase. It turns the race into a change of track. This is why the warp idea is not instantly rejected by the light limit. The light limit polices local motion in a given geometry. It does not forbid geometry from evolving. The universe already evolves its geometry. Expansion of space is one example. Gravitational waves are another example. In those waves, distances oscillate while matter remains nearly in freefall locally. Warp drive tries to replace an oscillation with a directed distortion. That is the step that becomes expensive. A directed distortion requires a stress pattern with direction. It must be held in place as it moves. It must be sustained. The equations demand an energy distribution that is not symmetric and not ordinary. The next small payoff is that the bubble's calm interior is not a guarantee of safety. The boundary is where the distortion is stored. The boundary is where curvature gradients live. The boundary is where light paths can be bent sharply. Any claim about controllable travel must survive the behavior of photons near that boundary. Photons do not care about intention. They follow the null path set by the metric. If the boundary produces horizon-like behavior, then signals can fail to reach the front. If the boundary produces strong frequency shifts, then incoming background light can become concentrated. These consequences arise from geometry alone. They arrive before any engineering story is told. A gentle transition follows. The warp bubble is now seen as a moving change in the metric that keeps local light speed intact. The next step is to decide what is truly moving when the bubble moves. The answer lies in how a travelling metric distortion is described and how local stillness can coexist with global displacement. The most disorienting feature of warp drive is that the ship is not the main thing in motion. The motion belongs to the metric pattern. The ship can remain almost at rest relative to its local interior. The geometry outside performs the translation. A quiet visual makes this feel less abstract. Imagine a calm hollow in a wide, drifting haze. The hollow is smooth. Its centre stays dark and still. Around it, the haze forms a thin shell with a sharper texture. The texture is not uniform. On one side, the haze layers compress into closely spaced bands. On the other side, the bands spread apart. The shell moves like a pulse through the haze. The hollow rides inside the pulse. Nothing inside needs to push. The shell's asymmetry does the carrying. The physical detail is the banding itself. It marks a spatial gradient, a change in the spacing rule across a narrow region. This section holds two concepts. One is local inertial motion. Local inertial means freefall with no felt acceleration. The other is a world line. A world line is the path of an object through space-time. In ordinary travel, a world line bends because acceleration is applied. In the warp idea, the ship's world line can remain close to a geodesic inside the bubble. A geodesic is the straightest possible path in a given geometry. One sentence defines it. Two sentences make it tangible. In flat space-time, a free object drifts on a straight world line. In curved space-time, a free object follows a path that looks curved in coordinates but is still straight in the geometric sense. One sentence says why it matters. If the bubble interior is arranged to be nearly flat, then the ship's geodesic can feel like simple drifting even while the bubble's centre changes location relative to faraway coordinates. The first payoff is immediate. High effective travel does not require high felt acceleration. That is the seductive part. Acceleration is what crushes bodies and structures in ordinary propulsion. Warp drive tries to avoid acceleration by keeping the interior nearly inertial. The ship does not need to build up enormous kinetic energy. It does not need to fight relativistic inertia growth. It simply remains inside the calm pocket. The second payoff follows. Avoiding acceleration does not mean avoiding relativistic consequences. The consequences relocate to the bubble boundary and to the global causal map. A calm interior is compatible with a severe exterior gradient. The interior comfort does not erase the boundary cost. An everyday analogy can keep the sense of carried without pushing while staying gentle. Consider a leaf floating in a slow eddy near a riverbank. The leaf can remain almost still relative to the water in the eddy. Yet the entire eddy can drift downstream as the broader current shifts the bankside flow. The leaf does not paddle. The pattern of flow carries it. This analogy must stay limited because space-time is not water. Still, it reveals the logical separation. The leaf is the ship. The eddy is the nearly flat interior. The broader flow pattern is the moving metric distortion. The first lesson is that local stillness and global displacement can coexist. The second lesson is that control belongs to the pattern, not to the leaf. If the eddy changes shape upstream in a way the leaf cannot signal to the leaf cannot steer, this becomes a serious issue in warp discussions. Now the limit of intuition arrives in a crisp form. In special relativity, velocity is a local concept between nearby observers. In general relativity, comparing velocities over large distances depends on how spacetime is curved in between. A ship can have zero local velocity relative to its immediate surroundings, while still showing large coordinate displacement relative to distant points. This does not mean it secretly violates a law. It means relative to distant points is not a single physical measurement without a chosen transport rule. To compare distant velocities, some convention is needed for how clocks and rulers are extended across curved space. Different choices can disagree. Only local comparisons are absolute. This is why claims like the bubble moves faster than light must always be treated as shorthand for a coordinate description. The physically protected statement is narrower. No local observer inside the bubble sees the ship outrun a nearby photon in the bubble interior. The next payoff comes from asking how the bubble itself moves. A bubble is not a solid object. It is a region where the metric takes a certain form. The motion is the shifting of where that form is located on the coordinate grid. In the Alcubierre construction, the metric is written to include a function that places the bubble center at a chosen position as a function of time. The bubble is then a traveling deformation. The deformation is sustained by a stress pattern in the shell. This is where the energy story enters again. A traveling deformation needs momentum flow in the stress-energy tensor. It cannot be supported by a static lump of ordinary mass alone. It requires pressures and energy fluxes arranged with direction. The shell is not only a place of curvature, it is a place where energy flow must have a very particular sign and distribution. A concrete physical detail helps. In many treatments, the shell is described as a torus-like distribution around the bubble, thinner in the direction of travel and thicker laterally. The exact shape can vary, but the lesson remains. The curvature is concentrated in a band. That band has a leading region and a trailing region. In those regions, the sign of certain energy components differs. The interior remains nearly flat. The shell holds the negative energy density in the simplest setup. The outside is nearly flat again far away. This layering is the architecture. Flat then steep, then flat. The gradients live in the steep layer. Everything difficult tends to live there as well. The scale shift can be made quiet. Over a laboratory scale, it is difficult to produce any measurable space-time curvature. Even massive objects create only tiny curvature at everyday distances. Warp drive asks for curvature gradients that are strong but confined. It asks for a pattern that is both intense and tidy. The mind can picture intensity as a deep pit. It can picture tidiness as a thin edge. Those two desires conflict. Strong curvature tends to produce strong tidal effects. Tidal means differential pull across a body. If curvature changes rapidly over small distances, then nearby geodesics diverge quickly. That divergence is what tides measure. A calm interior reduces tidal effects there, yet the boundary can still harbour them if the transition is sharp. This is the second limit of intuition. It is easy to imagine a clean bubble boundary like a soap film. In space-time, a sharp transition implies strong gradients, and strong gradients imply strong physical consequences for anything that tries to cross. A final payoff is about agency. If the ship is locally inertial, then ordinary control surfaces do not apply. Steering must occur by reshaping the bubble. But reshaping the bubble requires affecting the shell, especially the front region where contraction is arranged. If the front region becomes causally disconnected from the interior, then interior control fails. This is not yet proven in a single sentence. It is a geometric suspicion that becomes precise when photon paths are traced. The front edge can behave like a horizon. A horizon is a boundary beyond which signals cannot reach. One sentence defines it. Two sentences ground it. In a black hole, the horizon traps outward light. In a warp bubble, a horizon like cirrus can trap forward-directed signals from the interior. One sentence says why it matters. If signals cannot reach the region that must be altered to steer, then steering becomes impossible from within. This leads naturally to what must come next. The bubble is a moving geometry pattern. The ship can remain locally calm. The boundary holds the stress and the gradients. Photons are the strict tests of what is causally connected. The next section turns directly to light behavior near the shell because light reveals whether the bubble can communicate, navigate, or even remain safe when it moves through ambient radiation. Light is the most reliable witness of any warp bubble because it cannot be fooled by intention. It follows null paths set by the metric. If the metric is distorted, light records the distortion in its trajectory and in its frequency. A calm scene can make this precise. A field of dim, background glow fills space like a uniform haze. Through that haze, a warp bubble passes as a smooth oval cavity. The cavity looks clear. The boundary looks like a thin, shimmering rim, not because it shines on its own, but because the background behind it is displaced. Along the front rim, the background seems to compress into a narrow, bright seam. Along the rear rim, the background seems to thin and stretch. The physical detail is the seam itself. It is a band where rays converge and pile up. That pile-up is the first sign of trouble and also the first sign of testability. Two concepts carry this section. One is horizon-like causal structure. The other is frequency shift. Frequency shift means a photon changes color and energy because of geometry and motion. One sentence defines it. Two sentences ground it. In an expanding region, light tends to redshift sliding to longer wavelength and lower energy. In a contracting region, light tends to blue shift sliding to shorter wavelength and higher energy. One sentence says why it matters. A warp bubble contains both expansion and contraction around its shell, so it naturally produces both redshift and blue shift in different directions. The first payoff is about escape. Consider a photon emitted inside the bubble toward the front. Locally, it moves at light speed. Yet the front region of the bubble is defined by a contraction pattern that can advance away from the interior faster than the photon can close the distance. The photon is not slowing down locally. The geometry is retreating. The result is that the photon can fail to reach the front boundary. It becomes trapped behind a horizon-like surface inside the bubble. This payoff is quiet but decisive. If forward-directed light cannot reach the front edge, then neither can forward-directed control signals. The interior becomes causally cut off from the region that defines where the bubble is going. This is one of the strongest reasons warp drive starts to look like a space-time phenomenon rather than a vehicle. A second payoff arrives from looking at the opposite direction. Consider light approaching the bubble from outside from ahead. Those photons enter a region where space is being contracted in the bubble's direction of motion. Contraction tends to blue shift incoming light. Even very soft background photons can be shifted upward in energy. The shift depends on the strength of the contraction and on the relative motion of the bubble through the ambient frame. The deeper point is that the environment is never empty. Even deep interstellar space contains a bath of low-energy radiation. It contains sparse starlight. It contains energetic particles. A moving warp shell must interact with this background through its curvature. The interaction is not optional. Light cones and geodesics force it. An analogy can stay gentle and physical. Consider a thin glass prism moving through a fog of sunlight. The prism does not create the light. It gathers and redirects it. In some angles, it concentrates rays into a brighter line. In other angles, it spreads them into dimmer regions. The prism also shifts color slightly if it moves and if its material changes the path length differently for different wavelengths. A warp shell is not glass, but it plays a comparable geometric role. It is a moving lens made of curvature rather than matter. It can focus and defocus light. It can shift frequencies through gravitational-like and kinematic-like effects combined. The analogy highlights a key detail. Concentration can occur even when the background is weak. A thin fog can still become a bright seam when geometry gathers it. Now the limit of observation appears. Light behavior near a rapidly changing metric is difficult to compute with certainty when quantum effects are included. Classical general relativity traces null paths cleanly, yet the boundary gradients can be steep enough that semi-classical corrections matter. Semi-classical means quantum fields living on a classical curved background. One sentence defines it, two sentences ground it. In curved space-time, vacuum fluctuations respond to horizons and rapid changes producing particles in some settings. In cosmology and black hole physics, horizons are linked to particle creation and thermal-like spectra. One sentence says why it matters. If a warp bubble creates horizon-like regions, then quantum fields may respond with radiation or instability, altering the stress needed to maintain the bubble. A third payoff follows from accumulation. If forward-going photons emitted inside cannot escape, they can accumulate near the front region. If outside photons approaching from ahead are blue-shifted and focused, they can also accumulate at the leading shell. Accumulation means energy density grows in a thin region. Energy density is not passive in general relativity. It gravitates. It adds to curvature. The shell is already a region of extreme stress. Adding concentrated radiation can change the required stress balance. The bubble then becomes a feedback system. Geometry alters light, light alters energy distribution alters geometry. Even in ordinary settings, this loop exists, but it is weak. In a warped setting, it can become decisive. A single safe number can anchor the ambient radiation without turning sharp. The cosmic microwave background has a temperature of about 3 Kelvin. The exact value is not needed. The meaning is enough. It is a faint cold glow filling space. Under strong blue shift, cold photons can become much more energetic at the leading edge. The everyday comparison can stay calm. A gentle whisper can become a sharp note when compressed into a smaller timescale. The analogy is about compression, not about sound as a medium. The idea is that squeezing the wavelength increases energy. If the bubble compresses space ahead, it can squeeze incoming wavelengths in the same geometric sense. A further consequence is about release. If photons are trapped and piled up, then shutting down the bubble can release them. The bubble's boundary changes. Paths that were blocked can open. Stored radiation can burst outward. This is not a dramatic claim about explosions. It is a reminder that energy stored in concentrated fields remains real when geometry relaxes. A safe system would need a way to manage this release or avoid build-up in the first place. That management would require controlling the shell's gradients. It would require understanding how null paths behave during formation and dissipation. This is where the concept begins to look less like a single steady solution and more like a full dynamical process. A static metric on paper does not automatically include a safe way to turn it on and off. The section returns to the shimmering rim in the haze. The rim acts like a moving caustic. A caustic is a bright curve where rays concentrate. One sentence defines it, two sentences ground it. Caustics appear at the bottom of a pool when sunlight is focused by rippling water. They also appear in gravitational lensing when light is focused by curved spacetime. One sentence says why it matters. A warp shell is a designed curvature that can create caustics deliberately, and those caustics mark where energy density of radiation can rise. The transition is gentle and direct. Light behavior shows that warp drive is not only a question of geometry, it is also a question of energy conditions in the shell, because the shell must both create the curvature and survive the radiation and horizon effects that curvature induces. The next section turns fully to that accounting, and to why negative energy keeps appearing when the field equations are asked to support the bubble. Negative energy appears in warp drive discussions for the same reason a mirror shows what is missing as clearly as what is present. The field equations tie curvature to a local ledger of energy and stress. Ordinary matter fills that ledger with positive entries. A warp bubble asks for a specific kind of curvature that includes a deficit. The scene is a quiet, layered region in darkness. A broad, nearly uniform background remains calm and featureless. Through it drifts a smooth cavity with a thin surrounding band. The band has a strange structure. In one arc, the band tightens into a sharper gradient. In the opposite arc, it relaxes into a softer gradient. The cavity interior stays gentle and nearly flat. The thin band carries the burden of curvature. The first payoff sits in that band. If a bubble is engineered to compress distance ahead and expand distance behind the band, it must contain stresses that do more than pull inward. Something must push outward in a controlled way. In general relativity, pushing outward is not a separate force. It is a sign choice in the stress pattern that sources curvature. The bubble demands that sign change in a region that stays localized and stable. Two concepts hold the logic together here. One is stress energy. Stress energy is the local bookkeeping of energy density, momentum flow and pressure. The second is an energy condition. An energy condition is a rule that forbids certain stress patterns for ordinary matter. One sentence can pin the core. Many common energy conditions require that any observer measuring local energy finds a non-negative result. Two sentences make the meaning tangible. A region filled with dust radiation or ordinary fields registers as positive energy density for every local observer. Pressure can be large, but it does not flip the local sign into a sustained negative density. One sentence says why it matters. A warp bubble shell in its simplest form asks for a region where some observers measure negative energy density. The shell is not merely low energy, it is below the usual reference level for the vacuum in that region. The requirement is not introduced by preference, it is forced by the geometry the bubble needs. Contraction in front resembles an inward pull. Expansion behind resembles an outward push. In Einsteinian gravity, pressure and energy density both contribute to curvature. Positive pressure adds to gravitational attraction in many directions. To get a controlled repulsive effect in the needed directions, the stress pattern must include components that behave like tension rather than compression. Tension is pressure with the opposite sign. A thin shell dominated by tension can curve spacetime in an unusual way. The second payoff arrives quietly. Even without exotic particles, the mathematics demands a stress pattern that looks like stretched material with negative effective density in some frame. Ordinary fields resist applying that pattern at macroscopic scale in stable form. The bubble is allowed as a formal solution. The sourcing matter is the obstacle. A unique analogy can stay calm and physical. Consider a sealed elastic membrane enclosing a pocket of stillness in a turbulent fluid. The membrane remains smooth inside. Outside, the fluid presses from all sides. To make the membrane bulge forward without the contents moving, the membrane must carry a special distribution of tension. A region of higher tension pulls the membrane inward. A region of lower tension allows outward bulging. If the bulge must travel, the tension pattern must travel as well. The membrane does not create new material. It redistributes stress in a precise moving pattern. In the warp case, the membrane is not literal. The shell plays the same structural role in the equations. It is the place where stress must be arranged to guide curvature into a moving squeeze and release. The analogy highlights the key detail. The interior stays gentle only if the shell carries the hard work. A single safe number can anchor the difference between quantum hints and macroscopic demands. No negative energy effects are associated with tiny separations, often on the scale of a few micrometers. That distance is comparable to the width of a small dust grain. The scale shift is immediate and soft. A warp bubble useful for large travel would require a shell thickness and bubble radius that are many orders of magnitude larger. The gap between a micrometer and many kilometers is not a matter of patience. It is a different regime of physics. This is where the limit of intuition appears. It is tempting to treat negative energy as a resource that can be accumulated like a fluid. Quantum field theory does not behave that way. Negative energy in known settings appears as a relative deficit compared to a surrounding vacuum baseline. It also tends to be tied to boundaries, rapid changes, or special quantum states. There is no simple knob that deepens the deficit while keeping everything else quiet. The moment a deficit is made larger and longer, the theory pushes back with constraints that limit duration, spread, and stability. The idea of scaling a delicate micrometer effect into a macroscopic engineered shell is not forbidden by a single sentence. It is discouraged by the structure of the theory. The bubble requirement can be stated more concretely without equations. The shell must make space-time inside almost flat. It must also make spacetime outside almost flat far away. Between those regions, it must introduce a steep gradient that produces contraction ahead and expansion behind. That combination is what creates effective displacement without local superluminal motion. Yet the same combination tends to violate the simplest energy conditions. The shell needs a net pattern that in a local accounting behaves as if there is a region with less than zero energy density paired with large tensions. The third payoff is that negative energy is not a decorative detail. It is the direct shadow cast by the desired curvature pattern. Remove the shadow and the pattern collapses into an ordinary gravitational configuration that does not carry the cavity forward as intended. A visual anchor returns to the thin band but with a new detail. The band is imagined as stratified into layers. The inner layer keeps the interior calm. The middle layer holds the steep gradient. The outer layer smooths the transition back to ordinary space. In the middle layer, the sign of the stress pattern is the crucial feature. In ordinary matter, compression dominates. In the required shell tension, dominates in a directional way. That directional tension is what supports the asymmetric curvature. The band becomes the place where the universe demands payment. The payment is not only magnitude, it is also sign. The ledger must include a negative entry. Without it, the curvature cannot be shaped into the travelling bubble form. Another quiet limit follows from stability alone. Even if a suitable negative energy distribution exists, it must remain confined to a moving shell without dispersing. Classical fields tend to spread. Quantum fields tend to fluctuate. Sharp gradients invite back reaction. Back reaction is the response of fields and geometry to each other. One sentence defines it. 2 sentences ground it. If curvature becomes strong in a thin region, quantum fields can respond by producing additional stress and radiation. That extra stress changes the curvature that created it. One sentence says why it matters. A warp shell is a feedback system by construction. The very stresses that support it can be altered by the shell's own influence on the vacuum and on ambient radiation. This feedback makes a stable, long-lived negative energy shell even harder to justify within known physics. The section ends with a gentle narrowing of the problem. Negative energy keeps appearing because the desired curvature pattern demands it in the shell. Known physics offers only faint, tightly constrained examples of negative energy, and those examples live at tiny scales and short durations. The next step is to ask whether the negative requirement can be reduced, redistributed, or made compatible with strict conservation and stability. That question moves from geometry alone into the policing rules that quantum theory imposes on any negative entry in the ledger. The hardest part of warp drive is not speed, it is accounting. Energy does not vanish just because space-time is described with curved geometry. The calm hook is a simple image. A thin dim band crosses a wide, even glow, like a shadow laid across mist. The band looks stable for a moment. Then the glow on both sides subtly brightens as if the shadow must be paid for by a matching surplus nearby. The early takeaway is equally simple. A warp bubble can respect local energy conservation, yet still demand negative energy arranged in a way that known physics tightly restricts. This is where the idea shifts from a geometric curiosity to a test of whether the universe allows a sustained deficit at macroscopic scale. The first concept is local conservation. In general relativity, the stress pattern that sources curvature cannot behave arbitrarily from one moment to the next. Energy and momentum flow through space-time in a way that balances locally. Even in a changing geometry, the local ledger must close in each small region. A moving shell of stress is allowed in principle. It can carry energy density, momentum density, and pressure as a travelling distribution. Nothing in this local bookkeeping demands a global fuel tank in the ordinary sense. That sounds like freedom, yet it is a narrow kind of freedom. The second concept is global energy. In a curved and time-dependent spacetime, a single total energy for the whole universe is not always a clean quantity. In some geometries it can be defined. In others it depends on how the comparison is made at large distances. This is a limit of intuition. Flat space habits expect a single number that never changes. Curved spacetime can hide energy in geometry and can trade it between fields and curvature in ways that are hard to compress into one global figure. Yet this does not open a door to cheating. It shifts where the policing occurs. The policing becomes local and it becomes geometric. Any proposed shell must still be sourced by a physically allowed stress pattern everywhere it exists. The first payoff appears here. Local conservation does not rescue warp drive. It only prevents the most naive impossibilities. The shell still needs the wrong sign in the simplest models. The negative entry cannot be explained away by saying global energy is subtle. The sign shows up in local measurements along real paths. A second visual anchor settles in. The shell is imagined as a narrow layered rind around a calm cavity. The rind has a front arc where spacing compresses and a rear arc where spacing relaxes. If a small test photon tries to move forward from the cavity, its path can stall relative to the advancing front arc. This is not a new paradox. It is a reminder that the shell is already extreme in its causal structure. Now the third concept arrives. Quantum inequality means negative energy is limited in size, duration, and spread. One sentence defines it. Negative energy can appear, but it cannot be large and long-lived over a wide region. Two sentences ground it. In quantum field theory, a local deficit tends to be paired with a compensating surplus, often nearby in time or space. The deeper the deficit, the more sharply the compensation is forced. One sentence explains the relevance. A warp shell wants a deficit that is both deep enough to shape curvature and persistent enough to carry a bubble across distance. Quantum inequalities push back against both desires at once. A new analogy keeps this gentle. Consider a cool pocket forming inside a warm, restless layer of air. The pocket can exist briefly. It can exist over a small patch. Yet the deeper it becomes, the more violently it pulls surrounding air into motion. Mixing begins. The pocket is erased or broken into smaller fragments. The analogy is not about temperature as a force. It is about a deficit that provokes a restoring response. Negative energy behaves like a deficit in the vacuum structure. It can appear in small controlled ways. It tends to be accompanied by conditions that prevent it from becoming a stable macroscopic tool. The next payoff is quiet but firm. Even if a geometry only needs a moderate negative density, sustaining it over long times, and large volumes collides with quantum limits, the shell is not only a shape, it is a quantum state that must remain arranged. That state must resist relaxation. It must resist fluctuations. It must resist the tendency of deficits to be bounded by surpluses. A single number can anchor the scale without excitement. Quantum bounds often become sharp when durations approach about a millionth of a second for certain strong deficits. This is not a universal constant. It is a reminder of the mismatch in timescales. A bubble useful for large travel would need the shell to persist far longer than fleeting microphysical intervals. The scale shift is gentle. A millionth of a second is the time it takes light to cross a few hundred meters in empty space. A long journey requires persistence far beyond that. The mismatch does not prove impossibility. It makes the burden clear. A stable macroscopic negative region must either evade known bounds or be supported by new physics that changes the bounds. Another visual anchor returns to the dim band across the glow. The band now flickers. It deepens for an instant, then a bright ridge forms beside it, as if a wave must rise when a trough is forced. This is the common structure of quantum constraints. A negative pulse is balanced by positive pulses. The balance can be arranged in clever ways, but it remains a balance. Warp bubble proposals often try to soften the problem by reshaping the shell. A thicker shell spreads gradients. A smoother profile reduces peak curvature. A more elaborate shape function redistributes where the deficit sits. These changes can reduce extreme local requirements. They can reduce the total amount of negative energy integrated over the shell. The payoff here is that geometry matters. The original bubble is not the only mathematical form, yet another payoff follows immediately. Redistribution is not elimination. The sign problem remains in the simplest classical setting. The negative entry moves around, but it does not vanish. The shell still needs tension-like stress and deficit-like energy in some region to produce the desired push in the geometry. Now a deeper limit of observation arrives. The shell sits at the intersection of classical curvature and quantum fields. Classical calculations can describe a static metric as a clean object. Real fields fluctuate. If the shell creates horizon-like structure, quantum fields can respond with particle creation and stress. That response is back reaction. Back reaction means the quantum response changes the very geometry that triggered it. The effect is well known in other horizon settings. It is difficult to compute precisely in strong engineered gradients. This uncertainty is not a gap that grants permission, it is a warning sign. A proposal that leans on a delicate balance must survive the fact that the balance is disturbed by the fields living in that geometry. A final visual anchor closes the section. The bubble boundary is imagined as a faint ring where the background glow bends and narrows. Along the ring, thin streaks appear like fine cracks in a sheet of frost. The cracks represent instabilities. They are places where small fluctuations grow because the stress pattern is extreme. This is the last payoff for this part. Even if local conservation is satisfied, and even if a negative region can be formed briefly, maintaining a travelling shell that stays smooth is a separate demand. The shell must be stable against fluctuations. It must avoid turning its own gradients into radiation and noise. It must remain controllable while horizons threaten to isolate the front. These pressures do not arrive from one principle alone. They arrive as overlapping constraints that point in the same direction. The next step is not to argue about energy totals. It is to look at what happens to the ordering of events when a geometry allows effective superluminal connections. The discussion moves from the energy ledger to the causal map and to why time order becomes fragile when distance is reshaped too aggressively. Causality feels sturdy because it is repeated everywhere at every scale without exception. A cause comes first, an effect comes after. Warp drive threatens that ordering not by speeding a ship through space, but by changing which events can be linked at all. The calm scene is a pair of distant flashes in darkness. One flash occurs far away, and later another flash appears nearer. In ordinary spacetime, the nearer flash cannot be caused by the distant one, unless enough time passes for light to travel between them. The boundary of influence is still that expanding luminous sphere. Now, a warp bubble is imagined between the two flashes not as an object but as a moving distortion that shortens the route. The flashes begin to look uncomfortably close in the causal sense, even if they remain far in ordinary distance. The early takeaway is quiet and sharp. Effective fast and light links can turn the ordering of before and after into something that depends on the observer's steady motion, and that is where paradox enters. Two concepts hold the section. One is space-like separation. Space-like separation means no signal at or below light speed can connect two events. One sentence defines it. Two sentences ground it. If two flashes are space-like separated, then different inertial frames can disagree on which flash occurs first. Neither ordering is privileged. One sentence says why it matters. Causality is preserved because no influence can travel between them, so the disagreement cannot be used to create a contradiction. The second concept is an effective superluminal connection. This means a path exists through some geometry that links events faster than an ordinary light path would in flat space. One sentence defines it. Two sentences ground it. A warp bubble can create a route where a traveller stays locally below light speed, yet arrives sooner than a distant photon would through the unchanged space. The link looks superluminal when compared to ordinary flat routes. One sentence says why it matters. If space-like separated events become effectively connectable, then the frame-dependent ordering can be exploited to form a loop of influence. The first payoff is a clean statement without drama. Faster-than-light influence by any mechanism is sufficient to build a causal loop when combined with ordinary relative motion. The loop is called a closed time-like curve. One sentence defines it. A closed time-like curve is a path that returns to its own earlier time while always moving forward locally. Two sentences ground it. Along such a path, an event can influence conditions that lie in its own past. The traveller never locally moves backward in time, yet the global path closes. One sentence explains relevance. Warp metrics in some configurations allow effective superluminal travel, and that can be combined with ordinary motion of observers to build such loops in principle. A new analogy can keep the tone soft while making the structure visible. Imagine a broad, gently flowing conveyor of tiles in a large hall. Each tile moves at a modest speed. A person stepping from tile to tile never runs faster than a walking pace relative to the tile underfoot. Now imagine that some tiles are arranged so that stepping across a special corridor carries the person far across the hall much faster than walking on the floor. The corridor does not violate the local rule of walking pace. It changes the route. If there are two such corridors oriented differently, and if the hall itself has moving platforms that shift timing between regions, then it becomes possible to return to a starting point before the departure time as judged by someone standing elsewhere. The analogy is not literal physics. It captures the logical feature. The trouble does not require local backward steps. It requires a global route that allows a too-fast connection between regions that already disagree about simultaneity. A single safe number can anchor how small timing differences can matter. When relative speeds between observers are a significant fraction of light speed simultaneity, shifts become large. No digits are needed. The point is qualitative and stable. Even modest, effective superluminal connections can be amplified by chaining paths between moving frames. The scale shift lands gently. The paradox is not about travelling a little faster across a room. It is about linking distant events across space-time. The bigger the separation, the more room there is for frame-dependent ordering to matter. The limit of intuition appears because it is tempting to say if nothing locally exceeds light speed, causality is safe. That statement is true only for simple geometries. In curved space-time, local safety does not guarantee global safety. Global safety depends on the entire causal structure, which is how light cones tilt and connect across regions. A warp bubble can preserve ordinary light cones inside its interior, yet warp the arrangement of cones around its shell in a way that permits a global shortcut. The shortcut can cross from one region's future into another region's past, as judged by some observer once the geometry permits effective superluminal connections. The heart of the issue is that special relativity already allows different observers to disagree about time order for space-like separated events. Causality survives only because space-like separation prevents influence. If the separation is made influenceable, the disagreement becomes dangerous. A second payoff follows from a detail often overlooked. Even a one-way warp trip might be arranged to avoid a causal loop in a chosen external frame. Yet two trips or two bubbles moving relative to each other can reintroduce the loop. The fragility is structural. The geometry is not merely a road. It is a rearrangement of which events lie inside which other events' cones. If a bubble can be used to send a message that arrives too soon in some frame, then the message can be reflected back through another bubble and return to its origin before it was sent. This is the standard construction in relativity once superluminal influence exists. The precise steps depend on chosen speeds and separations, but the conclusion is robust. Effective superluminal travel is enough to endanger chronology. Now a gentle physical detail grounds the threat in geometry rather than in storytelling. A warp bubble often creates horizon-like boundaries. Those boundaries can prevent signals from reaching certain regions. At first, this seems like a safety feature. If the bubble cannot be controlled from inside, perhaps it also cannot be used to send signals in the problematic ways. Yet horizons are not a guarantee of chronology protection. They are a sign of causal distortion. The presence of horizons means the causal map is already strained. Moreover, control limitations do not necessarily prevent the existence of a loop in the geometry itself. A loop is about the existence of a path, not about comfort or steering. A third payoff arrives when quantum behavior is considered. Quantum fields are sensitive to causal structure. In spacetimes that permit closed time-like curves, many analyses find that vacuum fluctuations can grow without bound near the would-be chronology violation region. This can produce enormous stress energy that changes the geometry. The response is sometimes interpreted as chronology protection. It is not a moral principle. It is a dynamical instability. The geometry that would allow time loops becomes difficult to sustain because the quantum fields react violently. This is a limit of observation and calculation. Full quantum gravity is not yet complete. Yet the pattern is consistent across many semi-classical studies. Geometries that threaten chronology tend to trigger large back reaction that undermines the configuration. A final visual anchor settles the tone. The two flashes are revisited, and the warp distortion between them is imagined as a faint twist in the background grid. The twist is subtle at first. As the effective shortcut grows stronger, the twist deepens and the light cones around the shell tilt more sharply. The tilt is the geometric signature of the threat. It is the map of possible influence being bent. Causality is not broken by a single rule being ignored. It is broken by the map being folded so that paths can return to their own start in time. The transition to the next section is soft. If causality is fragile, then any realistic warp concept must confront not only energy and light behavior, but also control and observability. A bubble that isolates its interior with horizons may avoid some abuses, yet it may also become impossible to steer, monitor, or safely shut down. The next part turns to that practical face of the same geometry, and to whether a warp bubble can be interacted with at all once it exists. A warp bubble becomes unsettling when it is treated as something that must be used, not merely written. Use requires control. Control requires information. Information requires signals. Signals in practice are light. If light cannot cross the boundary in a balanced way, then a bubble is less like a vehicle and more like a sealed region of causality. The calm scene is a quiet oval cavity moving through a thin field of faint scattered glow. Outside the cavity, the glow forms a soft uniform background. Near the cavity rim, the glow bends into arcs, as if refracted by an invisible lens. At the front edge, the arcs tighten into a bright narrow band. At the rear edge, they stretch into dim filaments. The physical detail is the asymmetry of those filaments. It suggests that paths into the bubble and paths out of the bubble are not mirror images. That asymmetry is the heart of the control problem. Two concepts hold this section. One is horizon accessibility, the other is boundary crossing. Horizon accessibility means whether signals can reach a region at all from a given place. Boundary crossing means whether paths can move smoothly through the shell without extreme shifts. One sentence defines accessibility. A region is accessible if a light signal can reach it in finite time. Two sentences ground it. In ordinary space, any nearby region is accessible by a light, and control can be exercised by sending messages. In a horizon-forming geometry, some regions remain forever out of reach from certain locations. One sentence explains relevance. Warp bubbles can create horizon-like surfaces that make the front edge inaccessible from the interior. Boundary crossing adds a second layer. Even if a path exists, it might involve severe frequency shifts and tidal gradients that make crossing physically destructive. The first payoff is about steering. Steering a warp bubble means reshaping the shell so that the contraction region points toward a new direction. In ordinary motion, steering changes the ship's velocity. Here, steering changes the metric pattern. That pattern is concentrated in the shell, especially in the front region that defines the bubble's direction of travel. If signals from inside cannot reach that front region, then internal steering fails. This is not a matter of slow response. It is a causal disconnection. A command cannot be sent where no null path exists that carries it. The bubble becomes a geometry that carries its contents without allowing its contents to modify the carrying mechanism. A second payoff follows from stopping. In ordinary travel, stopping means applying a force opposite the motion-reducing kinetic energy. In warp travel, stopping means relaxing the metric distortion back toward ordinary spacetime. That relaxation must occur in the shell. If the shell cannot be adjusted from within, then stopping cannot be initiated from within. The bubble becomes like a locked process. It may be initiated by a mechanism, but once established, it may be difficult to halt without access to the relevant parts of the shell. This is a quiet but decisive way the idea changes character. It ceases to resemble piloting and begins to resemble initiating a space-time configuration that then evolves according to its own causal structure. An analogy can keep this in tissue without borrowing earlier ones. Imagine a long, slow closing iris of ice on a pond. A clear opening remains at the centre, while the rim thickens and refreezes. A small ripple generated at the centre travels outward, yet the rim is forming and moving as the ripple travels. If the rim closes faster than the ripple reaches it, the centre cannot touch the rim with its own signal. The centre remains calm. The rim controls the boundary. The analogy is about signal reach, not about ice as a medium. The lesson is that a moving boundary can outrun information from the interior, even when that information travels at the fastest allowed local speed. A warp bubble's front boundary can behave in that way. Boundary crossing creates a third payoff. Even if a bubble could be formed externally, entering it safely is not guaranteed. The shell is a region of steep gradients. A steep gradient means the metric changes rapidly over a short distance. Such changes can bend light sharply and can also produce tidal stresses on matter. Tidal stress is not acceleration of the whole object. It is differential acceleration between one side and the other. If the shell is thin and curvature is strong, the differential can become large across even small lengths. The limit of intuition appears here. It is easy to picture the shell as a smooth soap film that can be crossed like air. In geometry, a thin region can still hide extreme curvature. Crossing is not about pushing through a surface, it is about surviving a rapid change in the rules that define distance and time. A single safe number can anchor the idea of how quickly signals must move for navigation. Navigation in deep space relies on timing with precision far better than a second. No digits are needed beyond that. The point is stable. If a bubble blocks or distorts timing signals, then external references become unreliable. Inside the bubble, clocks can remain well behaved locally. Yet without balanced exchange of signals across the boundary, synchronization with the outside can fail. That failure is not a mere inconvenience. It undermines any statement like arrival occurs at this time in an external frame, because the internal record cannot be compared cleanly during travel. The scale shift lands softly. On Earth, even tiny timing errors translate into large position errors. Across interstellar distances, the demand on timing coherence grows even more severe, and a warp shell threatens that coherence. Observability adds another layer. Could an outside observer detect a bubble and track it? Classical reasoning suggests yes, because the shell behaves like a lens. A lensing signature could distort background light in a characteristic pattern. The pattern could resemble a moving region of strong shear, where star positions appear shifted and stretched around an invisible oval. The bubble could also create caustics bright arcs where rays concentrate, yet this detectability is double-edged. A bubble moving through a background of radiation and particles will also interact with that background. Incoming light could be blue shifted and focused at the front boundary. Outgoing light from inside could be trapped. If energy accumulates at the boundary, a bubble may produce transient bursts when its geometry changes. This returns to a key physical detail. The boundary is not only a geometric surface, it is a region where energy can pile up in fields and radiation. That pile-up can become an observational marker. It can also become a hazard. The limit of observation appears again, but in a different form. A full prediction of what an observer would see requires a fully specified dynamical model, including how the bubble is created, maintained, and dissipated. A static metric gives only a snapshot. The most dangerous behavior can occur during transitions when curvature changes quickly. In such times, frequency shifts can become extreme and quantum field responses can become significant. Without a complete theory of the controlling mechanism, the observational signature cannot be predicted with confidence. Yet the qualitative lesson remains. If the bubble contains horizon-like regions, then information flow is asymmetric and control is fundamentally constrained. The section ends with the cavity drifting through the glow, and the rim acting like a moving boundary where information seems to stick. The interior stays calm. The rim remains the active region. This returns to the same theme from a practical angle. Warp drive is less about pushing a ship and more about sustaining a space-time configuration. If that configuration isolates itself causally, it becomes difficult to steer, difficult to stop, and difficult to coordinate with any outside reference. The next step is to ask whether the entire idea can ever be more than a mathematical arrangement. That means returning to the deepest choice in the theory. Either the required exotic stress patterns exist in nature and can be stabilized, or the solution remains a formal possibility with no physical pathway. The next section gathers the constraints into that final question. A warp drive can be written as a clean geometric statement, yet still fail to exist as a stable thing in nature. The difference between those two outcomes is not a matter of optimism. It is a matter of whether the needed stress patterns can persist without triggering contradictions, instabilities, or runaway back reaction. The calm scene is a smooth oval cavity suspended in a wide, even darkness. Its boundary is traced only by how a faint background glow bends. The bend is orderly at first, then small irregular ripples appear along the rim. The ripples do not crash. They only grow slowly like fine wrinkles that spread along a thin film. The physical detail is the wrinkling itself. It is an image of instability. A configuration can satisfy equations and still be unstable to tiny disturbances. The early takeaway is quiet and precise. Warp drive remains an allowed solution of the field equations, but the combined demands of negative energy photon behavior and causal order make it difficult to treat as a stable, controllable process under known physics. Two concepts hold this section. One is physical realizability, the other is stability. Physical realizability means whether a solution can be sourced by physically allowed matter, fields, and can arise from plausible initial conditions. Stability means whether small perturbations remain small or grow. One sentence defines realizability. A realizable spacetime is not only consistent with equations, it can be produced by admissible sources and can survive small disturbances. Two sentences ground it. Many mathematical solutions exist that require matter with impossible properties or require exact symmetry that is destroyed by any small fluctuation. Those solutions remain valuable as tests, but they do not automatically describe something the universe can host. One sentence says why it matters. Warp drive sits precisely in this category because its geometry is easy to state, but its sourcing demands a stress pattern that ordinary matter does not provide at scale. The first payoff is about the role of energy conditions as filters. Energy conditions are not mere habits. They are the guardrails behind many theorems that prevent pathologies in general relativity. When energy conditions hold singularities and horizons behave in constrained ways, and chronology violations are harder to realize. When energy conditions are violated, spacetimes can permit traversable wormholes, time loops, and other exotic structures. Warp drive often requires violating at least some of these conditions. This does not prove impossibility. It explains why the same requirement keeps linking warp drive to the most exotic parts of the theory. The second payoff follows. If the only known way to source a bubble requires sustained violations, then the bubble is likely to inherit the same fragility and policing that those other exotic encounter, especially when quantum fields respond. A new analogy can keep the tone steady. Imagine a delicate pattern made in fine dry powder on a flat surface. The pattern is precise. The lines are sharp. It satisfies a design rule perfectly, yet it sits in a room where air is never completely still. The slightest vibration blurs the lines. The design is not forbidden by geometry, it is defeated by stability. Warp drive can be like that. A metric can be specified with sharp features. A physical world supplies fluctuations. Vacuum fluctuations, ambient radiation, and field perturbations act like the tiny air currents. If the required stress pattern is delicate, then it may be unstable in practice, even if it is exact on paper. A single safe number can anchor the age of the universe as a test of silence. The universe is about 14 billion years old. The exact figure is not the point. The point is that space-time has existed for a long time, without observable macroscopic warp-like engineered bubbles appearing naturally. This silence is not a proof, it is a constraint. If warp bubbles were easy to form from known fields, then extreme astrophysical environments might have formed them accidentally. Compact objects, early universe conditions, or violent mergers would have provided opportunities. Yet observed phenomena show curvature expansion and horizons in familiar forms. They do not show localized traveling cavities with lens-like signatures and horizon behavior detached from gravitational collapse. The payoff here is that observational conservatism matters. Nature realizes only a small subset of mathematically permitted spacetimes, and it tends to realize those that emerge robustly from stable matter and stable evolution. The limit of observation appears in a careful form. A lack of evidence is not evidence of absence unless the signal would be unmistakable and the search would be complete. The sky is vast. Detection is limited. Yet warp bubble signatures, if strong, could plausibly include distinctive lensing patterns and unusual radiation transients due to frequency shifts and accumulation at boundaries. Whether such signals have been searched for systematically is an open practical question. Even so, the larger point stands. Realizability is not settled by equations alone. It is settled by whether stable sources exist and whether the configuration can form and persist without self-destruction. The third payoff concerns the dynamical route the problem of turning a bubble on and off. A static solution does not provide a creation history. To form a bubble from ordinary initial conditions, the stress pattern must be assembled. As it is assembled, the causal structure changes. Horizons may form, light paths may be trapped, frequency shifts may grow, quantum fields may respond to the forming horizon with radiation. Even if a steady bubble is mathematically consistent, the formation process may generate lethal byproducts or instabilities that prevent reaching the steady state. Dissipation has the same risk in reverse. If energy accumulates in trapped radiation, then relaxing the bubble can release that stored energy. A stable, safe process must control these transitions, not only the steady configuration. A visual anchor returns to the wrinkling rim. Each wrinkle is imagined as a small deviation in the shell profile. If the shell must maintain a precise gradient to keep the interior calm and the exterior distortion aligned, then a wrinkle can scatter null paths unpredictably. Scattering can change where radiation accumulates. Radiation changes the stress balance. The loop can amplify the wrinkle. This is the stability story in slow motion. The bubble is not only a structure, it is a coupled system. Geometry influences fields. Fields influence geometry. A stable bubble would need to sit at a robust equilibrium of this coupled system. Known examples of a robust equilibrium in strong gravity are limited. Black hole horizons are robust, but they come with causal isolation and singularity-related constraints. Cosmic expansion is robust, but it is global and not shaped locally. Warp bubbles ask for robustness without those familiar stabilizers. A fourth payoff links the constraints into one quiet conclusion. The same features that make warp drive attractive local calm and effective shortcut are produced by extreme boundary behavior. Extreme boundary behavior is exactly where energy conditions are strained, where horizons appear, and where quantum back reaction is strongest. The concept selects the most difficult region of the theory and asks it to remain tame. That is why modern discussions often treat warp drive as a stress test. If a deeper theory of space-time exists, it must explain whether such engineered distortions are allowed, and if not, which principle forbids them without contradiction. The transition is gentle and forward. If warp drive is a stress test, the next step is to widen perspective. Some constraints come from local physics, others come from the global structure of the universe and from how space-time behaves on the largest scales. The next section moves outward, looking at expansion vacuum energy, and why cosmic acceleration is not the same kind of push a warp bubble needs, even though both involve space-time changing. Cosmic expansion proves that space-time can change in a way that resembles faster than light separation, yet it does not offer the same tool a warp bubble needs. The calm scene is a wide, faint fog of light that seems almost uniform. Within the fog, small dim points keep their local spacing like beads embedded in a soft gel. Over time, the beads drift farther apart, not because they slide through the gel, but because the gel itself subtly swells between them. The physical detail is the swelling, which is smooth and everywhere at once. It has no sharp boundary. It has no shell. The early takeaway is simple. The universe's expansion shows that the metric can evolve, but that evolution is global and gentle, while a warp drive requires a local directional shell-confined distortion with steep gradients. Two concepts carry this section. One is expansion driven by energy with negative pressure. The other is localization. Negative pressure means a stress pattern that makes expansion accelerate. One sentence defines it. Negative pressure is a kind of tension-like stress that causes spacetime to expand faster rather than slow down. Two sentences ground it. In cosmology, a uniform energy component can have pressure that is negative in the equations producing accelerated expansion of space. This does not require negative energy density. The energy density can remain positive while the pressure term drives acceleration. One sentence says why it matters. Warp bubbles often require negative energy density in a localized shell, not merely negative pressure spread uniformly. Localization is the second concept. Localization means shaping a field or stress pattern into a bounded region with controllable edges. One sentence defines it. A localized configuration has a boundary where the field changes from strong to weak over a finite distance. Two sentences ground it. A warp bubble depends on a shell, a place where curvature is concentrated. Cosmological acceleration by contrast appears smooth and uniform on large scales, without sharp gradients or movable edges. One sentence says why it matters. A uniform push cannot be aimed like a bubble, and it cannot carry a protected cavity through space as a directed wave. The first payoff is the key distinction between space expands and space is engineered into a travelling distortion. Expansion in cosmology is described by a scale factor, a number that changes with time and stretches distances between comoving points. In a homogeneous expansion, every region stretches similarly at large scale. The expansion does not create a front edge that outruns signals from the interior. It does not create a localized horizon structure like a moving bubble can. There are cosmological horizons, but they are tied to global expansion and observation limits, not to a thin shell moving through a background. The warp bubble requires something more surgical. It requires contraction in front and expansion behind. That is not what uniform expansion provides. Uniform expansion does not create a preferred direction at a point. A bubble must. A second payoff comes from the idea of vacuum energy. Vacuum energy is the baseline energy density associated with empty space in quantum field theory, often discussed in connection with cosmic acceleration. One sentence defines it. Vacuum energy is an energy density present even when no particles are present. Two sentences ground it. If vacuum energy behaves like a constant background, it can act as a smooth source that influences the expansion rate of the universe. It does not clump strongly under gravity in the way ordinary matter does. One sentence says why it matters. A source that does not clump cannot easily be shaped into the localized gradients a warp bubble needs. Even if vacuum energy exists, it behaves like a uniform field, not a sculptable shell. A gentle analogy helps without repeating earlier ones. Imagine a loaf of dough rising evenly. Points on the dough surface move apart as the dough expands. No point needs to crawl. The material between points grows. This is like cosmic expansion at large scales. Now imagine trying to form a travelling dimple that carries a dry pocket through the dough without deforming the pocket's interior. That dimple would require controlled tension and compression in a moving ring. Dough does not support that ring without tearing or relaxing. The analogy is about uniform versus localized deformation. The universe seems to allow the uniform version readily. The localized directional version is what the warp idea demands. A single safe number can anchor the scale mismatch. The observable universe spans tens of billions of light years. Cosmic acceleration acts across those enormous distances and becomes relevant at large scales. Warp drive aims to operate across distances like light years, while remaining confined to a bubble perhaps measured in kilometers. The scale shift is gentle but firm. A phenomenon that emerges as a global average can be smooth precisely because it is not asked to have sharp edges. A bubble is almost nothing but edges. The boundary is where the metric changes quickly. That is where energy conditions become strained. That is where photon behavior becomes extreme. Cosmic acceleration does not require that boundary architecture, so it avoids many of the bubble's problems. The limit of intuition appears, because it is tempting to say, if the universe does it, a machine can do it. Nature does many things by being large and patient. It also does many things only as uniform trends rather than as localized tools. A black hole is a natural concentration of curvature, but it comes with horizons and causal isolation. Cosmic expansion is a natural evolution of the metric, but it lacks direction and localization. Warp drive tries to combine the benefits of both. It wants strong localized curvature without collapse, and it wants controlled expansion and contraction without global consequences. This combination is exactly what triggers the need for exotic stress patterns. It is not enough to borrow the word expansion. The tensor structure of the stress energy must match the desired curvature. Uniform negative pressure is not the same tensor pattern as a shell with negative energy density and directional tension. A third payoff comes from considering why cosmic acceleration is not easily harvested. Even if a uniform background energy exists, turning it into a gradient is not a simple act of engineering. Gradients imply differences from place to place. Differences from place to place imply a mechanism that breaks uniformity. In known physics, fields that can be shaped into localized configurations tend to carry additional energy costs and tend to radiate or relax. If vacuum energy is a constant, there is no lower energy state to pull it into a pocket. If it is a field with dynamic shaping, it may be possible in principle but would require excitations that come with their own stresses and instabilities. The bubble's negative energy requirement does not dissolve into just used dark energy. Dark energy, as currently described, is not a controllable substance. It is a large-scale parameter of the universe's evolution. A visual anchor returns to the swelling fog with beads embedded. The swelling remains smooth and quiet. There is no moving rim. There is no sharp band. That absence is meaningful. It is a reminder that the universe's most dramatic metric changes can be gentle at local scales. A commoving observer does not feel expansion as a force in a small neighborhood. The same is true for the bubble interior in warp proposals. Yet the bubble adds a shell with a sharp gradient, and that sharpness is where the difficulty concentrates. Cosmic expansion offers no example of a stable traveling sharp-edge metric distortion that carries a protected cavity. The transition is soft. Cosmic behavior clarifies what warp drive is not. It is not simply space expands. It is a carefully shaped localized metric wave, with contraction and expansion in opposite directions. The next section returns inward to the shell, again focusing on the most physical consequences of steep gradients. Tidal behavior stability against perturbations, and how a shell might tear itself apart become the next calm checkpoint. A warp bubble can feel gentle at its center, and still be violent at its edge, because curvature is not measured by how calm a region looks, but by how quickly the geometry changes across space. The calm hook is a simple boundary image. A thin dark ring floats in a faint glow. Inside the ring, the glow is smooth and quiet. Outside the ring, the glow is smooth and quiet again. Only the ring itself shows structure. It is layered like a narrow ridge. The physical detail is that layering a stacked gradient that marks a rapid change in the metric over a short distance. The early takeaway is direct. The thin shell that makes warp drive attractive also concentrates the strongest tidal and stability challenges, and those challenges grow sharper as the shell is made thinner and stronger. Two concepts carry this section. One is tidal stress. The other is perturbation growth. Tidal stress means differential stretching and squeezing across an extended object due to curvature gradients. One sentence defines it. Tidal stress is the difference in freefall motion between nearby points. Two sentences ground it. In a weak gravitational field nearby, freefall paths stay nearly parallel. In a strong gradient, nearby freefall paths diverge or converge quickly, stretching an object along one direction and compressing it along another. One sentence says why it matters. A warp shell is a region built from gradients, so it naturally raises tidal questions at the boundary, even if the interior stays calm. Perturbation growth is the second concept. One sentence defines it. A perturbation is a small deviation from a perfect configuration, and growth means the deviation amplifies over time. Two sentences ground it. Real fields fluctuate, and any engineered distribution will have small imperfections. In an unstable system, those imperfections do not fade. They feed on the system's structure and become larger distortions. One sentence says why it matters. A warp shell that depends on a precise stress pattern may be fragile if small deviations change light, focusing, change energy accumulation, and then feed back into the shell. The first payoff is about the boundary being the true engine room. The interior is designed to be nearly flat. That design reduces internal tides and keeps local physics ordinary. Yet the bubble must connect that interior to the external universe. It does so through a shell where the metric changes rapidly. The strength of that change determines how much effective distance reshaping occurs. A stronger reshaping requires a stronger gradient. A stronger gradient tends to produce stronger tidal stress. This is the central trade. The bubble's usefulness grows with boundary intensity, while survivability and stability often shrink. The second payoff follows. Making the shell thinner can reduce the total amount of exotic stress integrated over volume in some models, but thinning also increases peak gradients. Peak gradients are what photons and tides respond to most strongly. A thinner shell can be more efficient on paper, yet more violent locally. The trade does not disappear, it moves. A new analogy stays gentle and physical. Consider a sheet of flexible material stretched across a frame with a narrow crease pressed into it. Far from the crease, the sheet is smooth. Close to the crease, the slope changes rapidly. A small bead rolling across the sheet accelerates and turns sharply at the crease because the local slope changes. The bead is a stand-in for a geodesic. In space-time, geodesics are the natural paths of free motion. The shell's steep gradient is the crease. Even if a region inside the crease is flat, crossing the crease exposes the bead to the sharpest change. The analogy highlights the physical detail. It is not the flat regions that cause trouble. It is the narrow transition zone where the rule changes quickly. A single safe number can anchor how thinness changes effects without invoking equations. If a shell's thickness is reduced by a factor of 10, while the overall distortion strength is held similar, gradients can grow roughly by a comparable factor in the simplest geometric sense. The exact scaling depends on the profile, but the direction is robust. The scale shift lands softly. A gentle slope over a long distance feels mild. The same change packed into a short distance becomes steep. Curvature gradients behave like that packing. This is why boundary design becomes the central engineering issue in any speculative warp discussion. It is not only how much exotic energy, it is how sharply is it arranged. The limit of intuition appears in the temptation to equate no acceleration felt with no stress present. In freefall, a body can feel weightless even in strong gravity if it's small enough and the gradient is weak across it. The feeling of calm is local. Tidal stress is non-local within the object. It depends on differences from one end to the other. A warp interior can be made calm, yet the shell can still create extreme tidal gradients for anything that tries to cross it, and potentially for anything near the boundary. Calmness at a point does not guarantee safety across a finite size. This is why the shell's structure matters in physical detail. If the curvature is confined to a band with rapid change, then nearby world lines can shear apart. Shear is a distortion where neighbouring paths slide relative to each other. In many field systems, shear and large gradients are where instabilities seed. The third payoff links tides to light behaviour. If the shell acts like a strong lens, then small shape imperfections can shift where rays focus. Where rays focus, radiation energy density rises. Where radiation energy density rises, additional stress appears. That additional stress modifies curvature. Curvature then modifies focusing again. This loop can amplify a tiny imperfection. A wrinkle on the boundary can become a hotspot for radiation accumulation. That hotspot changes the stress pattern, making the wrinkle deeper. The system becomes prone to runaway localization. This is not a guaranteed outcome. It is a plausible instability channel in any geometry that focuses rays strongly while depending on a delicate stress balance. A quiet visual anchor returns to the thin ring with layers. In the ring, small ripples are imagined as travelling along the circumference. Each ripple is a perturbation. Some ripples damp out in stable systems. Others grow if the system provides a mechanism that feeds them. In a warp shell, the feeding mechanism can be the coupling between curvature and trapped or blue-shifted radiation. The shell can also couple to vacuum fluctuations if horizon-like structure forms. These couplings mean the shell is not isolated from the quantum and radiative environment. Even deep interstellar space is not empty of fields. The shell interacts with whatever is present, and the interaction can act as a source of noise that seeds perturbations. Another limit of observation enters. Determining stability requires a full dynamical analysis, not only a static metric. It requires specifying the fields that source the shell and how those fields evolve under perturbations. Without a complete theory of the exotic stresses, provider stability cannot be confirmed. Yet the qualitative picture remains valuable. Systems with steep gradients and horizon-like causal structure are often difficult to stabilize. In known physics, horizons tend to be associated with thermal-like radiation and back reaction. Strong lenses tend to produce caustics where energy densities spike. These are warning signs in the warp context because the shell combines both features. A final payoff focuses on what stability would demand. A stable bubble would likely need a thick enough boundary to keep peak gradients moderate. It would need a profile that avoids strong caustics in the forward direction. It would need a way to bleed off accumulated radiation without catastrophic release. It would need a sourcing field that provides negative energy density and tension-like stresses without itself becoming unstable. Each of these demands is already challenging alone. Together they form a tight box of requirements. The transition is gentle and forward. If the shell must be thick, smooth, and dynamically controlled, then the question returns to what kind of matter or field could supply such a stress pattern without violating quantum bounds or creating causal loops. The next section turns back to the policing of time order, not as a philosophical worry, but as a physical feedback. If a bubble configuration threatens chronology, quantum fields may respond in a way that destabilizes it, and that response may be the deepest reason such bubbles fail to persist. Chronology protection is not a rule written on a wall. It is a possibility that the universe responds dynamically when a geometry threatens to let influence loop back on itself. Warp drive presses near that boundary because effective superluminal connections can be combined into causal loops, and the same boundary regions that enable those connections often resemble horizons that excite quantum fields. The calm scene is a narrow corridor of distorted background light, like a soft twist in a grid. The twist is subtle at first, then deepens into a tighter bend as if the grid is being folded toward itself. Where the fold becomes tightest, the background glow brightens into a thin seam. The physical detail is the seam at the fold. It suggests energy concentrating where causal structure strains. The early takeaway is quiet and precise. Attempts to create geometries that allow time loops tend to invite large quantum back reaction near the would-be violation region, and that back reaction can destroy the geometry that made the loop possible. Two concepts hold this section. One is semi-classical back reaction. The other is chronology protection as instability. Semi-classical back reaction means quantum fields contribute stress energy that alters classical curvature. One sentence defines it. Quantum fluctuations in a curved geometry can produce real energy densities that then change the geometry. Two sentences ground it. Near horizons, vacuum states can differ for different observers, and this difference can appear as thermal-like radiation. When curvature changes rapidly, particle creation can occur, adding stress energy where none was put by hand. One sentence says why it matters. A warp shell that produces horizon-like regions can trigger quantum field responses that add unpredictable stress to the shell. Chronology protection as instability is the second concept. One sentence defines it. Chronology protection is the idea that the laws of physics prevent macroscopic time loops by making loop-forming geometries unstable. Two sentences ground it. In many analyses, as a geometry approaches allowing a closed time-like curve, quantum stress energy near the critical region grows very large. That growth can warp space-time in a way that removes the would-be loop or collapses the region into a different structure. One sentence explains relevance. Warp drive proposals that skirt the edge of causality may trigger the same kind of runaway response, especially if they rely on sustained energy condition violations. The first payoff is about the nature of the threat. Causality problems do not need a traveller carrying a message. The geometry itself can permit a path that returns to an earlier event. Once such a path exists, physics must answer whether it is allowed to persist. Classical general relativity often answers, yes, the equations allow it as long as the stress pattern is admitted. Quantum fields add the second voice. They are sensitive to the global causal structure. If paths exist that loop through time, then field modes can wrap around the loop in self-reinforcing ways. That wrapping can amplify fluctuations. The amplified fluctuations produce large stress energy. The stress energy modifies curvature. The curvature can then change or eliminate the loop. The payoff is that chronology protection, if real, is not a separate law. It is a feedback process. The universe would protect causality by making causality-violating configurations self-destruct. A new analogy can keep this gentle. Consider a thin strand of material being twisted tighter and tighter. At low twist it holds shape. At higher twist kinks form. The kinks concentrate strain into narrow points. Eventually the strand buckles or snaps at the kink. The twist is like the attempt to fold causal structure into a loop. The kink is like the region where closed time-like behavior would first appear. The snap is like back reaction that prevents the loop from stabilizing. The analogy is about concentration. Systems under strain often fail at the point where strain concentrates, not where the system looks calm. A single safe number can anchor the sensitivity of quantum fields without becoming technical. Vacuum fluctuations exist at all scales, but their influence on curvature is usually negligible. The reason is that positive and negative fluctuations average out. Yet near a horizon or rapidly changing geometry, the averaging can fail for certain observers. That failure can turn a subtle effect into an accumulated stress. The scale shift lands softly. Over ordinary distances and times, the vacuum looks smooth. Near a critical causal boundary, the vacuum can behave as if it has a temperature and a flux. The presence of that flux is not about the vacuum being hot everywhere. It is about the observer-dependent slicing of modes. In a warp shell with horizon-like regions, similar observer-dependent slicing can appear. The second payoff connects this to the warp bubble's control problem. A bubble that is already hard to steer from inside because of horizons is also a bubble, where the quantum state of fields can differ sharply across the boundary. That difference can produce stress on the boundary itself. The boundary stress is exactly what must be held in a precise profile to keep the interior calm and the exterior distortion aligned. Quantum back reaction becomes a source of noise and drift in that profile. If the bubble is near a causality threshold, the back reaction can become large. The bubble then becomes less like a stable engineered field and more like a critical system poised to run away. The limit of observation appears because the full calculation requires a complete theory of quantum fields in a dynamically evolving, strongly curved spacetime with exotic stress sources. Such a calculation is beyond current controlled methods in many cases. Yet some qualitative features recur in many settings. Horizons are associated with radiation. Rapid metric changes are associated with particle creation. Closed time-like curves are associated with divergent or large stress energy in semi-classical treatments. These are not isolated claims. They are repeated patterns in theoretical analysis. The cautious statement is enough. If warp drive requires horizons and energy condition violations, it likely enters the regime where these patterns matter. A third payoff is about a narrow form of safety that also undermines usefulness. A warp bubble could be constrained so that it never allows a round-trip time loop in any frame. That would require limiting effective superluminal connections or restricting relative motion between bubbles. Such restrictions can make the bubble practically unusable for flexible travel. They can also require the bubble to remain causally isolated in ways that prevent signals from escaping or steering adjustments from propagating. The bubble would then be safe by being locked. This is a pattern that appears again and again in the warp discussion. Avoiding paradox tends to reduce control. Increasing control tends to open doors to paradox. This trade is not proven as a universal theorem, it is a recurring tension from the causal structure. A visual anchor returns to the twisted grid and the bright seam. The seam now pulses gently like a region where energy density rises when the fold tightens. The pulse is a metaphor for back-reaction building as the configuration nears a causality threshold. The geometry is not static, it reacts. The environment is not passive, it answers with field stress. In such a coupled system, the most sensitive point is the boundary where the causal map changes most rapidly, which in the warp bubble is the shell and its horizon-like features. The section ends with a soft pivot. Chronology threats are not merely philosophical, they can act as physical triggers for instability through quantum back reaction. If that is true, then warp drive might be filtered out by the universe in the same way other causality-violating structures appear filtered. The next section widens perspective one last time, not toward grand promises, but toward what warp drive teaches about the nature of space-time. It becomes a map of where geometry is flexible and where it resists, and that map can be valuable even if the bubble itself never becomes a stable object in nature. Even if warp drive never becomes a physical device, it remains a precise lens for understanding what space-time allows and what it refuses. It draws a boundary line through three ideas at once. Geometry can change, light must still define local influence, quantum fields still police the extremes. The calm scene is a wide region of near-uniform darkness faintly stippled with a soft background glow. Across this field, three patterns appear one after another. First, a gentle broad swell like a slow wave in the glow. Second, a brief thin ripple like a passing tremor. Third, a sharp travelling cavity with a narrow shell like a cutout moving through the glow. The physical detail is that only the third pattern has a crisp edge. The swell has no boundary. The ripple has no persistent boundary. The cavity depends on its boundary. The early takeaway is quiet. The universe tolerates metric change in ways that are smooth or transient, but it resists sharp, sustained directional distortions that require exotic stress and that threaten causal structure. Two concepts hold the section. One is natural versus engineered curvature. The other is constraint layering. Natural curvature means curvature arising from ordinary matter radiation and large-scale cosmic components. Engineered curvature means a carefully shaped configuration designed to produce a specific causal effect. One sentence defines the contrast. Natural curvature emerges from stable sources and evolves through robust dynamics. Engineered curvature demands precise stress patterns with sharp gradients and sustained control. Two sentences ground it. Gravitational lensing arises from the steady presence of mass distributions that are stable over long times, producing smooth deflection patterns. Gravitational waves arise from violent events, but they pass as travelling ripples and do not require sustained exotic stress in a thin shell. One sentence says why it matters. Warp drive is an engineered curvature concept. Its defining feature is a protected interior and a travelling shell that maintains a particular asymmetric pattern over time. Constraint layering is the second concept. One sentence defines it. Constraint layering means multiple independent physical principles restrict the same configuration in overlapping ways. Two sentences ground it. For warp bubbles, energy conditions restrict the stress sources. Photon behavior restricts horizons and frequency shifts at the boundary. Causal structure restricts effective superluminal links and time loop formation. One sentence says why it matters. When independent constraints converge, the configuration becomes less likely to be realizable without new physics that changes more than one principle at once. The first payoff is a clean reframing. Warp drive does not challenge the speed of light as a number. It challenges the relationship between distance-time and influence. The speed of light remains the local conversion between space and time. The bubble tries to alter distance by altering the metric. That move invites immediate scrutiny from photons and from energy conditions. The scrutiny is not optional because photons are the messengers and energy is the source. This is why the same obstacles recur across decades of analysis. Negative energy persists. Horizons persist. Causality concerns persist. The repetition is not stubbornness. It is a sign that the bubble is pressing on structural features of the theory. A new analogy can keep this calm. Imagine a map drawn on a soft sheet. The sheet can be stretched gently across a frame. It can be tapped so that ripples run across it. These are like cosmic expansion and gravitational waves. Now imagine trying to fold a moving pocket into the sheet that carries a region without stretching the region itself, while also keeping the fold's edge thin and stable. This is like a warp bubble. The first two deformations happen easily because they do not demand a long-lived sharp boundary that must keep a protected pocket intact. The third deformation demands a boundary that behaves like a moving seam. Seams are where tearing begins. The analogy points to boundary dependence as the core difficulty. A single safe number can anchor the idea of precision without invoking instruments. A warp bubble would need its shell profile to remain stable to far better than a percent across its full extent to avoid shifting caustics and runaway focusing. The exact figure is not important. The magnitude of the requirement is. Sharp-edge systems are sensitive. Small imperfections produce large changes in where rays converge. In a bubble where rays converge is where energy accumulates. Where energy accumulates is where the stress pattern changes. The scale shift lands gently. Over small laboratory scales, controlling field profiles is difficult but possible within limited regimes. Over macroscopic scales with exotic stress and strong curvature control demands become far more severe. The limit of observation appears in a reflective form. Modern physics can test general relativity with remarkable precision in weak and moderate fields. It can also probe quantum field theory with extraordinary accuracy in flat or gently curved settings. Warp drive sits in a corner where both theories must be used together at strong gradients. That corner is one of the least explored experimentally. This does not mean the corner is free, it means uncertainty is higher. Yet uncertainty does not favour warp drive automatically. It also favours the possibility that new constraints appear not fewer. A deeper quantum theory of spacetime could forbid such shells more decisively, or it could allow new forms of stress that make them possible. Either way, warp drive clarifies what any deeper theory must explain. The second payoff is about what warp drive teaches even as a no. If warp bubbles are impossible under known physics, the reason is informative. It would mean that the universe protects local causality not only through the light limit, but also through limits on which geometries can be supported by real stress sources. It would mean that negative energy is permitted only in forms too constrained to be used for macroscopic metric engineering. It would mean that horizons and back reaction are not rare quirks but central stabilizers of the causal order. In that sense, warp drive becomes a probe of the protective architecture of spacetime. The third payoff is about what would need to change for a yes. It would not be enough to discover a new material with high energy density. The issue is not magnitude alone. The issue is sign distribution stability and causal accessibility. A successful theory would need to allow sustained localized negative energy density, or an equivalent effective stress pattern. It would need to manage horizon-like disconnections so that control remains possible. It would need to prevent time loop formation, or provide a consistent causal structure that remains stable under quantum fields. These are not separate tasks, they are interlocked. A change to one part of the framework tends to tug on the others. Any new physics that opens the door would need to do so without collapsing the coherence of the rest of reality. because the rest of reality is already confirmed by countless observations in calmer regimes. A final visual anchor returns to the three patterns in the glow. The swell remains smooth and unthreatening. The ripple passes and leaves no seam. The travelling cavity remains the only one that demands a sharp rim. The rim keeps trying to wrinkle. The wrinkles keep trying to focus light. The focused light keeps trying to change the rim. The image is calm, but it contains the whole story of constraint layering. The universe seems comfortable with metric change that does not rely on a persistent seam. The seam is where the difficult demands collect. The transition is gentle and settling. The next section does not chase new promises. It gathers the core logic into a quiet resolution. Warp drive remains an allowed mathematical solution, and that allowance is valuable because it reveals the flexibility of space-time. Yet the known constraints suggest that flexibility is guarded by deeper rules tied to energy photons and causal order. The final section rests on that boundary, leaving the topic with steadiness rather than suspense. Warp drive begins as a geometric whisper and ends as a question about the universe's self-consistency. The calm hook is a simple contrast. A vast darkness holds a faint background glow that barely changes. Within it, a smooth cavity appears for a moment, outlined only by how the glow bends at a thin rim. The cavity looks calm. The rim looks tense. The early takeaway is quiet and complete. General relativity permits warp-like metrics, but known physics makes them hard to realize because the shell demands exotic stress, complex photon behavior, and a causal structure that easily becomes fragile. The full arc can settle into three clear ideas without tightening the tone. First, the light limit remains local. Nothing with mass or information outruns light through ordinary space in its immediate neighbourhood. Warp drive does not try to win that race. It changes the route by changing the metric. That is why it fits inside the mathematical framework. Second, the metric is not a decorative field. It is the structure that light and matter follow. If the metric is distorted into a travelling bubble, light becomes the strict test. Photon paths reveal horizons. Photon frequencies reveal blue shift and red shift. Photon focusing reveals where energy can accumulate at boundaries. Third, the source of the distortion is not optional. Curvature is tied to stress energy. In the simplest warp constructions, the stress energy must include negative energy density, or equivalently exotic tension-like stresses in a shell. Quantum theory allows small deficits in special states, but it constrains their size, duration, and spread. The shell that would carry a macroscopic bubble is far beyond the regime where negative energy is easily available. A calm visual returns us to the bubble boundary and adds one last physical detail. The rim is imagined as a layered band thick enough to avoid an infinitely sharp gradient, yet still steep compared to the calm interior and the calm exterior. Along the leading arc, rays of background light bend and tighten into a narrow caustic line. Along the trailing arc, rays spread into dim threads. This asymmetry is the simplest geometric sign that the bubble is doing work. It is also the simplest sign that the bubble must face consequences. A caustic is a place where rays concentrate. Concentration raises energy density. Energy density affects curvature. The boundary becomes a coupled system where geometry and fields react to each other. Even without any added narrative, that coupling is a real constraint. The first payoff of the closing is that negative energy is not a random annoyance. It is the shadow cast by the required curvature pattern. Contraction ahead and expansion behind are not symmetric demands. They require directional stress. That stress in known treatments violates the usual energy conditions. Those energy conditions are not merely cultural preferences. They are the assumptions behind many stability and causality results in relativity. When they are violated, spacetimes can permit wormholes and time loops on paper. Warp drive belongs to the same family. It is permitted, and it is immediately pushed toward the edge cases. The second payoff is that horizons are not rare side effects. They are natural outcomes of trying to move a shell faster than internal signals can reach parts of it. If the front edge of the bubble advances in the causal sense, faster than light from the interior can catch it, the interior cannot communicate with that region. This threatens steering and stopping. It also isolates the system in a way that resembles an event horizon's most practical feature loss of two-way exchange. A bubble that isolates its own control surfaces becomes less like a craft and more like a locked spacetime phenomenon. The calm interior then becomes an ambiguous comfort. It is comfort inside a configuration that may not accept intervention once established. The third payoff is that causality is not a secondary philosophical worry. It is baked into the structure of space-like separation and frame-dependent time ordering. If effective superluminal connections are possible, then loops of influence become possible in principle. Many semi-classical analyses suggest that as geometry approaches chronology violation, quantum stress energy can grow large and destabilize the configuration. If chronology protection is real in any form, it may appear as a physical instability rather than a law written in isolation. That instability would be the universe's way of refusing to let time order become a tool. It would not need to forbid warp metrics at the level of equations. It would need only to prevent them from persisting as stable systems. A gentle scale shift can close the argument without sharpening it. On the smallest scale, quantum fluctuations allow brief bounded departures from classical energy expectations. On the largest scales, cosmic expansion shows that the metric can evolve and even produce faster-than-light separation of distant regions without local violations. Warp drive asks for both at once. It asks for quantum-like exotic stress in a macroscopic engineered shell. It asks for cosmic-like metric change in a localized directed wave. Known physics tolerates the small exceptions and the large smooth trends. It resists the attempt to make a sharp travelling seam that carries a protected cavity while remaining controllable and causally safe. The limit of observation can be stated softly. A definitive answer requires deeper understanding of quantum space-time in strong engineered curvature. Present theories can describe static metrics. They can describe quantum fields in many curved settings. They struggle most in the combined regime of strong gradients horizons and exotic stress sources. That regime is where warp drive lives. This uncertainty does not promise feasibility. It marks a boundary of present knowledge. Yet even at that boundary, the existing patterns are coherent. Negative energy is constrained. Light reveals horizon behavior. Causality threatens loops. Stability is hard when a boundary must remain precise and moving. The closing visual returns to the faint background glow now undisturbed. The cavity fades away, leaving only smooth darkness and slow uniformity. The lesson remains in the absence. Space-time is flexible, but it behaves as if that flexibility is guarded. It bends around mass. It ripples under violent events. It expands across the universe. It rarely, if ever, forms sharp travelling seams that can be guided at will. Warp drive is valuable because it makes that guarding visible. It shows that the speed of light is not merely a speed, but a local boundary tied to causality. It shows that geometry is not free, but sourced by stress that must obey quantum limits. It shows that attempts to sculpt distance can pull on the ordering of time itself. The final transition is a landing rather than a doorway. The idea of warp drive remains a quiet map of the edge of the known framework. That map can be held gently, does not demand belief. It invites patience with what the universe allows and what it refuses. The background glow stays even. The grid of space-time remains calm. The night keeps its steady pace.